Okay, we're extending the concept that we learned of solving inequalities in Chapter 3, Section 3 into a more problem-solving model, and that's called linear programming. So what we're going to do is we're going to take that concept of solving or graphing systems of inequalities and we're going to turn that into a real problem. Linear programming is a process to determine the most effective choice in a system of inequalities, imagining that all the solutions are possible choices. 1 1's a choice, 2 2's a choice. We did a mixed nuts roasted peanuts problem where there was lots of different amounts of cases of mixed nuts and roasted peanuts you could purchase, but you know that you can only spend $500 or $600 and have 500 cans and packages total. So there are some constraints, there's some things that you couldn't do, and we're going to talk about how to do the process and how to graph this on in this chapter 3, section 4. A constraint that you need to know when I'm talking about what a constraint is basically each inequality is a constraint. In the mixed nuts and roasted peanuts, you had to have less than $600. You had to have fewer than 500 of the packages and cans. Vertices. Vertices are how many intersection or how many points the inequalities intersect at. So if there's 4 inequalities, there's going to be 4 vertices because those inequalities are intersecting at 4 different places. If there's 3 inequalities, there would be 3 vertices. And we're going to look at those vertices in a second. So we're going to do this problem. So we're going to graph each system of constraints. These are all of our constraints. We have 4 of them. 1, 2, 3, 4. We're going to find the vertices of those constraints and then find the value that maximize and minimize the objective function. Now, this is the profit or cost function. This is going to tell me, based on how much I sell my mixed nuts or roasted peanuts for, how much I'm going to make. In this case, it's a little different than the mixed nuts and roasted peanuts, but your X is 4 times as profitable as your Y. Basically, if your Y was $1 a piece, then your X would be $4 a piece. And so in order to find the profit, you take however many X's you sold and multiply by 4, and take however many Y's you sold, and then add that profit together to find your maximum or your total profit. So we're going to see which vertex maximizes our profit. So we're going to graph it, and that means graph each system of inequalities. We have 1, 2 inequalities, and they're both less than, so we would shade below. The intersections are right here. The other 2 stipulations is, in general terms, when we're talking about inequalities, we know we're in the first quadrant. In the case of our mixed nuts roasted peanuts problem, we knew that we could not have -1 mixed nuts and 2 roasted peanuts. That doesn't make sense because you can't have -1 cases. But all of these are possible solutions. We could have 2 and 2, we could have 1 and 1, we could have 1 and 4, we could have 4 and 1. That would represent 4 of this thing. In our old example, is 4 mixed nuts and 2 roasted peanuts. In fact, that is one of the vertexes. Other vertexes, you can see there's 1, 2, 3, 4. Other vertexes are 5, 0, 0, 0, and 0, 6. So the vertexes are basically found after you graph them and find where all the intersection points of your constraints are. One was this line saying that it's got to be greater than 0, y's got to be greater than 0, x has got to be greater than 0, and then the other 2 inequalities. And so the shaded region, they all intersect right here. Those are vertices. The last thing we need to do to use those vertices is plug them into our profit equation, which was 4x plus y. So 0, 0 means I'm making $0 off of the 4, or if I have 0 cases, so 4 times 0 is 0, plus 0 cases of the other. This one's 4 times 5 plus 0, which is 20. This one's 4 times 4 plus 2, which is 18. So in actuality, the best, the maximizing of our profit is going to be found if we plug in 5, or if we basically buy 5 of the first thing and 0 of the second. We're going to make the most money out of it. The only maximum profits can come from vertices. You can't have a maximum profit somewhere in this just free floating zone, because you're always going to get more if you go towards a certain point, and those points are the vertex. So like, let's say that this was the maximum. This point would yield a certain amount, but as soon as you got closer and closer to this point and chose different values, you're going to increase your profit until you get to that maximum. If this was, let's see, actually this was a profit this time, so all the increases are going to point towards this way. So if you went from here to here, if you tried 1, 0, and then 2, 0, you're going to increase your value. But if you went from 3, 0 to 3, 1, you're kind of going away from that, so you're going to decrease your value. So those vertices are basically the maximum potential that you can get out of this, and you know that one of them is going to get you the maximum amount. Okay, so you try. Graph these systems of constraints, name all the vertices. The values of x and y that minimize the objective function are the amount that you get that's least in your cost. So you also have a cost equation. Sometimes you have a profit equation. This one you have a cost equation. So here's your constraints. Graph them, find the vertices, and then plug into each one. And tell me which one is the minimum, or which is the point, which is the vertex that minimizes your cost. Go ahead and finish that, and pause it now, and when you're done, move on. Okay, for further help on these problems, you're going to be on page 138, numbers 4 through